Hello, physics students. It's Mr. Kennedy here. Hope everybody's doing great. Hope everybody's nice and safe and healthy. Today I'm going to take you through a few basic ideas in circuit electricity. We talked a little bit about basic charges and how forces between charges happen. But today we're going to look at something where these charges actually move and some of the rules that happen when they move. And these are usually pretty easy. Some of these basic electrical ideas are pretty easy. But I'm going to take you through some of the basics of it. So imagine here that we have a wire. So this is a wire, like just imagine it's a tube right here. And inside that wire, let's just say we have charges flowing. Now, in reality, it's electrons that flow. It's the negative charges that flow. But we usually talk about the fact of positive charges flowing. For this course, it's not really going to matter. But let's just say we have charges here, and those charges are going to flow down the wire. They're going to go this way, head to the right. So when this happens, when we get charges that flow, we call that current. And that current, we use a lot of analogies with this, that it's a lot like water. The analogy breaks down a little bit, but this idea that we have these charges flowing, we kind of treat it like it's water flowing. It's not perfect, but it works pretty well. Now we denote current by the symbol I. Current is change in charge over change in time. How much charge, how many of these charges pass by a certain point in a given amount of time. And again, you could think of this like water in a sense. Now, charge, remember, is measured in coulombs. The time will be measured in seconds. And the current is measured in amperes. Although nobody really says amperes, they usually say amps. So coulombs is measured in C for coulombs, seconds there, and capital A for amperes. And usually, like I said, this is a pretty simple calculation that you can do. For instance, if we were to take a look at a simple calculation with it, let's say we said that during this wire, in a time of 2 seconds, we saw that in this wire we had 10 coulombs pass by. And you will see, in these wires, quite a bit of current can actually flow through. But let's say we said 10 coulombs passed by in 2 seconds. Well, if we want to find out how much current that is, the current is change in charge over change in time. If we said we had 10 coulombs pass by in 2 seconds, then we see we have 5 amps. That's 5 amps of current that actually flows by. So this is how to do some simple calculations to find out how much current is actually present when in a circuit. But there's a little bit more of a fundamental rule. It's more of a rule than a law, even though it has the title of law. And we're going to use that here now. This is kind of your big one for current electricity. But let's do a quick diagram first. If I do a diagram of a circuit, this symbol is a battery. This one right here. This long plate means the positive terminal of the battery. This is the negative terminal of the battery. These lines here are just wires. So if I take a battery and I hook it up to this little squiggly thing, is known as a resistor. It's something that is going to slow the current down or inhibit the current as things are going. So this is a complete circuit. Now, this resistor could be represented by, or could mean something else too. Like let's say we put a light bulb here. This battery might light up the light bulb. And the battery will have a certain amount of voltage to it, and that voltage is energy. Now, you probably heard of things like a 1.5 volt battery, which is the battery in your calculator, a 9 volt battery, or a 6 volt battery. That is what gives the energy to the circuit. So this right here, this battery has a certain voltage. and we just call that V for voltage. That is what the energy is of the circuit. This right here, this resistance, or the resistor has a resistance that we call R. That is how much resistance is giving to current in the circuit. If I just took this voltage from the battery and I just hook up the wire without any resistance in it, wires do have resistance in it, but just a little bit of resistance, then just tons of current would flow, the battery would be drained out really quickly, and that would be the end of it. But there is a rule for this. The rule for this is something called Ohm's law. And what it says is that the voltage is equal to the current times the resistance. Now, let's go through the units here first, and then we'll make a few comparisons and things. First of all, voltage, pretty easy. That one's actually measured in volts, with a capital letter V as a symbol. We just talked about current. That's what current is. And that's measured in amps, or amperes. And then resistance, that's measured in ohms. And an ohm is a uppercase omega. That's the symbol. Kind of a little squiggly thing. You may need some practice drawing your ohms. Now, I'm not sure if I told you this in class or not, but my father was an electrician. And one of the things that he had, and I still can't find it, I've looked everywhere for it, he had a coin. And the coin actually helped you solve Ohm's law. On one side of the coin was this. So this is the coin right here. It had a voltage there, current, and resistance. And what you would do with this coin is you would just cover up the thing that you were trying to find. Are you trying to find voltage? Cover it up. It's I times R. Are you trying to find current? Covered up. It's V over R. Are you trying to find resistance? Covered up. It's V over I. It was a nice way to help you solve for what the missing piece you're trying to find in Ohm's law. And this law will help you figure out a bunch of things about what's going on in the circuit. Maybe you know the voltage, maybe you know the resistance. Now you can find the current, let's say. So this was a handy thing. But the problem is that most people don't have a really good grasp of what these pieces are when they first start working with it. So let me give you an analogy. And it's not perfect, but it's just an analogy that may help. This equation is very similar to F equals ma. This is not a perfect analogy yet, but I'm going to reverse this a little bit. And instead of F equals ma, I'm going to say F equals am. So if you're trying to think about like what Ohm's law really means, here's a way to think about it. The voltage in the circuit is, in a sense, like the force that makes things move. It's really the energy, it's really the energy per charge, but it's really the force that makes things move. The resistance is what stops that flow from happening. So it reminds me a lot of mass, that resistance and mass are the same, because remember, mass resists when you try to actually move an object. And then the current is a lot like what's happening in the wire. Those particles are moving, they start to move, kind of like things would start to accelerate when you have it. So I like to think of V equals IR and F equals MA as they're not perfect analogies, but they're similar to each other. And so Ohm's law is a pretty big rule. As a matter of fact, for students in my AP class, when I tell them when they're taking the electricity and magnetism test, if they go through that test and don't use Ohm's law, they made a pretty big mistake. Well, there's another big rule here, and then we'll get into solving some problems. And it actually deals with the other side of the coin that my father had when he was an electrician. So the other piece of this is about power. And we've talked about power as work over time. And we said that power was measured in watts. Work is joules, time is seconds. But power can actually be measured another way with electricity. Power is also the voltage times the current. So these two quantities multiplied together, which is why we like them measured that way, gives you a measure of power. So when you're talking about, let's say, a 60-watt light bulb, you take the voltage in it, take the current in it, that's what you're really talking about. So that same idea with light bulbs, even this one right here, you're talking about the voltage times the current. But there's actually something you can do with this. If you look and remember Ohm's law, V equals IR, well, V is equal to IR, so in place of V, put IR, and you have I times R times I. So that means it's I squared R. That is also what the power is in the circuit. So if you have V times I, use that. If you have I and R, use that. But then notice that I can do the same thing with I here, because I is V over R, so then I'll put that in, and I have V squared over R. So I really have three different versions of power. Power is V times I, power is I squared R, or power is V squared over R. However, you could just use Ohm's law with any of them, so it really doesn't matter. But on the back of that coin that my father had, he actually had a really similar thing to Ohm's law. So he had this on the back. So power is V times I. If you want to find power, cover it up, it's V times I. If you want to find voltage, it's power over current. If you want to find current, it's power over voltage. So any of those things are going to help you find out what the power is. So let's do a really, really quick review of the units involved, and then we'll take a look at a problem. So charge, that's measured in coulombs, C. Current, that's measured in amperes, A. Voltage, that's measured in volts, V. Resistance, that's measured in ohms, symbol for ohm there. And then power, which we already knew from before, is measured in watts. So a lot of new units that we just kind of threw at you. So I just wanted to do a quick review. So charge, current, voltage, resistance, and power. But let's do a really simple problem here. So let's say we take, there's a battery, there's your resistor. So let's say we have a 1.5 volt battery, and this is a 10 ohm resistor. Now this 1.5 volt battery, that could be a C battery, that could be a D battery, that could be a AAA, that could be a AA. They're all 1.5 volts. This 10 ohm resistor, this would be a really common resistor that we would have in the lab if we actually did an experiment with it. And the resistor just looks like a little piece of ceramic that you're going to see in some of your lab stuff that you do. But in this question here, I've got a 1.5 volt battery, I've got a 10 ohm resistor. I'd like to know, what's the current in the circuit first? How much current is flowing in there? I'd like to know, what's the power that's in the circuit? What kind of power output does this have? And then, how much charge passes in 1 minute? How much charge passes by in 1 minute? Okay, so let's actually figure out what these things are. The current. I have the voltage and I have the resistance, and I want to find the current. So I use Ohm's law. I can go back, look at my little algebra coin here. I want to find the current. Current is voltage divided by resistance. So that means that it's 1.5 volts divided by 10 ohms. And what that tells me is that the current, 1.5 divided by 10, is 0.15 amps. So that's the current that actually flows in the circuit. So we've got the current. Now let's see if we could figure out the power. So with the power, I'm going to put up here, by the way, I'm going to put that we have 0.15 amps flowing in that circuit. So now let's figure out the power. The power, we can go back and use the other side of the coin. Power is voltage times current. I want to find the power. I can cover that up and find that pretty nicely, but power is voltage times current. So the voltage is 1.5 volts multiplied by 0.15 amps. And let's see what we can get here. So if we notice, this is 1.5 times 0.15, which is really similar to 15 times 15. So 15 times 15 is 225. It would be watts. But then notice we are 2 decimal places back here and 1 decimal place back from here. So this should be 0.225 because 1, 2, and 1. So 1, 2, 3. So 0.225 watts. So that would be a pretty small power output. But again, it's a small battery, and that's a pretty small current that actually passes through there. So we have the current, we have the power output of this circuit. Now let's find out how much charge passes by in 1 minute. So if we want to find the charge, we know that current is charge over time. We already know the current. That's 0.15 amps. We're looking for the charge, how much charge passes by. We can't use minutes though. We have to put that in seconds because this is an SI unit and needs to be brought over into seconds. So we have the charge would be, to find the charge, it's 0.15 times 60. That's 0.15 amps times 60 seconds. And what we're going to see here is if we do a little bit of mental math, you've got 6 times 15. 6 times 15 gets you 6 times 15 gets you 90. We'll put coulombs there, but we're not quite done because now 6 times 15 gets you 90. We have 1 extra 0 because of that, because of the 60, but then we have to take 2 away because we are 2 decimal places back, so 1, 2. So this should be 9 coulombs. So we would get 9 coulombs to pass by. That's a lot of charge from such a small battery, but this, remember, is allowing quite a bit of charge to actually flow once this starts. So this should help you through some of the basic ideas in circuits. Ohm's law is a pretty big law throughout electricity. And again, I found that students using those little coins and covering it up really helps because they're just not familiar with the whole manipulation of these ideas yet. So if you have questions, please feel free to let me know. I hope everybody's doing great and you can get started on doing some of your circuit work. Pretty soon we'll be talking about how to put these resistors in series and parallel. All right, everybody. Hope you had a great day.